Okay, so now what you are going to do is you are going to which color? Huh. So f of x, this is also a piecewise function, more very lot, okay, a lot than usual you will be having this one only, which is 2x minus 1. So x is less than or equal to, then x is greater than 1, then x is continuous at 1 or not is the question. Okay, then after that one this question we are going to discuss. Then after this, another one question we are going to discuss. Okay, then you will be feeling kind of comfortable with all these concepts. Okay, so what did I say? What is the formula? So what is the formula? That is limit x tends to a minus f of minus x should be equal to limit where x tends to a plus f of x plus should be equal to f of a. Yes, right. So this is what our formula is. So first I'm going to find for f of a, which means at x is equal to 1. Okay, f of a, because here a is equal to x, which is equal to 1. Okay, so at this point only you are going to find. Okay, so limit x tends to 1. Sorry, this is just f of x, right? So f of x which is equal to f of 1 which is equal to, for this which piecewise function you have to choose? You have to choose this one function only, because here only equal to 1 is there and you are choosing at 1 only. So you have to choose this formula, so which is equal to 1 plus 1 which is equal to 2. Okay, next is at x minus you are going to choose. So 1 minus you are going to write. So limit x tends to 1 minus f of 1 minus is equal to f of x. X is equal to, first what is the formula that you are going to choose? See, it is 1 minus, that means it is going to be less than 1. So x is going to be less than 1. So x is less than, so this formula only you have to use, which is x plus 1. Now, so here you have to also put like this, limit x tends to 1 minus, then use this one which is x plus 1, okay, which is equal to, now in place of x we are going to substitute 1, so it is also 1 plus 1 which is equal to 2. Then after that at 1 plus you take, okay, 1 plus, if you take now, then limit x tends to 1 plus, okay, f of x plus, which is equal to limit x tends to 1 plus, here if you notice here x should be greater than 1, so which is 2x minus 1. Okay, so 2x minus 1, now substitute in place of x 1, so then it will be 2 into 1 minus 1 which is equal to 1. So here you can see that, f of a is not equal to limit, sorry, first f of a is equal to limit x tends to a minus f of a minus is equal to f of x minus okay, which is not equal to limit x tends to a plus f of a, okay, which is not equal to, okay. So from this you can conclude that this is discontinuous. Okay, so conclusion is discontinuous. Now next question that what we are going to do is this question. So they have given that it is continuous at x is equal to minus 2. So which means, okay, so x is equal to minus 2, then f of minus 2 which is, okay, wait, f of x is equal to f of minus 2, which is equal to k. Okay, so they have given that this is continuous, and you can see that their limit will be existing. Okay, when they have given that their limit will be existing and it is also continuous, that means f of x is equal to limit where x tends to a f of a. Okay. So now get f of, so this one we are going to get, so limit x tends to a. Here you need not to put a plus or a minus because here already limit exists. So when you know that limit already exists, you need not to do a plus and a minus, and you need not to show that limit exists, and then you need not to equate that. And as I said that already, you have to know limits concept, then only you will be understanding this. Okay, so limit x tends to a, which is equal, okay, f of x, which is equal to, now what you are going to choose? You are going to choose this one. So here this is going to be 2. Okay, minus 2, that 2. Okay, so limit x tends to minus 2, this value you put, that is going to be x square minus 6 minus 6 whole divided by x plus 6. Wait one second, another question is correct or wrong? Wait. Oh god, it's not changing. Question is correct. And also note this one example. This one example you are going to also see. Okay. This is also one type of discontinuity, I will say. No, this is not one type of discontinuity. I'm sorry. This is not one type of discontinuity. Well, there are some types of discontinuity. Even in our book, they have given one example for finite discontinuity. Sorry, removable discontinuity. Okay, so coming to here, so just not differentiate it, factorize it. So then that means minus 6 when you multiply, and when you add it should be minus 1. So which is going to be minus 6 and plus 1. Okay. When you multiply minus 6 and when you add, you will be getting, no, that's not the case. Yes, when you are adding, you will be getting not minus 1, you will be getting minus 5. But minus 3 and plus 2. Okay, minus 3 and plus 2. When you add that, you will be getting minus 1, and when you multiply them, then you will be getting minus 6. Okay, so where you can write it as, each and every time to write limit, I'm feeling kind of lazy, so I'll do one thing. Like this you will put and you will write. So factorize them. So it will be x square minus 3x plus 2x minus 6 whole divided by x plus 6, right? So when you are taking common, what can you take? You will write like this. Okay, say no, like the same thing I have written. 3 and then 2. Okay, here minus should be coming. Oh god, again looks like this. Okay, now it's all correct. Now just factorize them. So while factorizing, what you will be getting? You will be getting which is equal to x, you can take common now. So x plus 2 minus 3, which is x plus 2 whole divided by x plus, wait, the question is wrong, that is why I got out. Here 6 will not come, here also 6 will not come. So 2, 2, 2. Okay, so you can again rewrite it as, which is equal to which is equal to, so you can again rewrite it as x plus 2 into x minus 3 whole divided by x plus 2. So you can cancel x plus 2, and you will be having x minus 3. Okay, then you will be having x minus 3. So in place of x you can put minus 2. So that means minus, okay, so minus 2 minus 3 is equal to minus 5. Okay, so you have got this as minus 5. So that means what is this? This and this will be equal, right? This and this will be equal, right? So that means k is equal to minus 5. Okay, k is equal to minus 5. This is easy question. Okay, this is also easy question. Now we shall do one JEE sum. Okay, then with that this will be kind of easy. Okay, don't worry, this sum, the word JEE might mean like, okay, it's kind of tough sum, that really it is not. All you have to do is you have to use your brain. Just look at the question, many of you guys will answer it just by looking at it. Okay, so f of x is equal to greatest integer function of x minus greatest integer function of, okay, greatest integer function of x by 4. So they are asking in the questions even. See, always look at the options. After reading question, don't directly solve those sums. Okay, look at the options. Okay, then you will be getting some sort of idea. Then you do the sum. Okay, you can see that clearly. Okay, well, I have not written any options, and I don't think I'll be showing on the any page. I will not edit it. So they are asking that whether it is continuous at a 4 or it is not. Okay, so the doubt point is 4. Okay, so first is f of x you are going to find. So here x is equal to 4. So f of 4, which is equal to greatest integer function of 4 minus 4 by 4. So greatest integer function of 4 is equal to 4 only. So it will be 4 minus, this is going to be 1. Okay, greatest integer function of 1 is going to be 1 only. So which is equal to 3. Okay, which is equal to 3. Next is limit where x tends to 4 minus f of x minus, so which is equal to limit x tends to 4 minus. Okay, so now you do this, which is going to be greatest integer function of x. So in place of this you are going to write 4 minus, okay, 4 minus whole divided by 4. So from here you have to get some knowledge about greatest integer function. I will say this one. So when you are having something like 0.9, it will be converted into 0. Okay, when it is greatest integer function. When you are having something like 3.9, then it will be converted into 3. Okay, so see, 4 minus, now what? It is some number which is very slightly, okay, very slightly lesser than 4. Okay, a number which is very slightly lesser than 4. That means it will be approximately 3.9999999. Okay, but since it is inside the greatest integer function, okay, even though this is very literally it is equal to 4, but you should not take it as 4, because of this function will be converted into 3. Okay, because of this function will be converted into 3. So which is equal to 3 minus, you can see that it is going to be 3.99999 by 4, which will be 0 point something. Okay, it should be 0 point something. So since it is 0 point something, even if it is like 0.111 or 0.99999, you need not to take care, it will be 0 only. Okay, it will be 0 only. So you can put here 0, which is equal to 3. Okay, next is limit x tends to 4 plus, where f of x plus is equal to limit x tends to 4 plus. Okay, so here now you check, here it will be 4 plus minus 4 plus by 4, which is equal to what? 4 plus, which means what? Which means like it will be right 4.001, like that, can be something like that. Okay, but because of this greatest integer function, it will be converted to 4. Okay, so in place of this you can write 4. Then see, here it is 4 plus divided by something. Okay, it is 4 plus divided by 4. Sorry, it is not something. 4 plus divided by 4. So it will be like you can take like 4.11 whole divided by 4, the greatest integer function. It will be approximately something like 1 point something something. Okay, so if it is 1 point something, then greatest integer function will convert it into 1. Okay, minus 1, which is equal to 3. You can see in all 3 cases it is 3. So hence it is continuous at 4. Okay, hence it is continuous at 4. we did all the sums. Okay, like we did some sums, right? Okay. And this is actually a question that was asked in 2019. Okay, there are still a lot of sums that we can do, but since I have an examination tomorrow, we will do only concepts. Okay. Next, what do we have to discuss? Next concept that we have to discuss is types of discontinuity. We have to discuss. Then continuity at an interval first we will complete fully. Okay. See, continuity at an interval. Okay. So already it is proven a few points. Okay. Already it is proven a few things. That is, okay, for already it is proven all those things is which I am saying, right? For them it is proven. Which color? This color will be correct, right? So see, for polynomial functions, for trigonometric, for trigonometric, then for exponential, then for exponential, then for logarithmic, okay, for all these, okay, polynomial, trigonometric, exponential, logarithmic, not for modulus. So modulus also it is okay, but at their respective domain. Okay, so but for modulus they have not given, but okay, see, for polynomial, for trigonometric, for exponential, and for logarithmic, it is okay, it is continuous. Oh wow, color changed. Continuous at their respective domain. It is already proven. Okay, so you can see, you can ask me a question like, for tan, how it is? See, it is discontinuous now for tan. Then how can I say it? Okay, this is a common question. Well, what do they say? They say that it is continuous at its respective domain. So what is the domain of tan? It is actually all real numbers excluding 2n minus 1 into pi by 2. Okay, this is what the domain. Correct. Okay, so this is what the domain of tan is. So at this point, so that means exclude this one. Okay, then exclude this one. Other than this, it is what? It is continuous, right? So that is why they said it. Okay, so remaining for this, okay, other than this, there are also some other, right? For modulus they have not given. Then for gift they have not given, greatest integer function. Then for fractional function they have not given. Like that, there are some functions, right? For that at all, what? See, for that you have to check. Okay, for that you have to check at the place where the definition changes. Okay, first is to check. Okay, where to check? Which color? Dark green. To check. So where to check? At the place wherever the definition is changing. Okay, so definition changes. Then at boundary points. For this we will be doing some boundary points. Okay, see, definition changes in sense, you just look at this one. See, here x, for x which is not equal to 2, you have one function. Okay, but for x which is equal to minus 2, sorry, when x is not equal to minus 2, you have one function, and when x is equal to minus 2, you have another function. See, here also it changes, not here. Here you see, for where x is less than or equal to 1, you have one function, and where x is greater than 1, you have another function. So the definition changes. So wherever the definition is changing, those points you have to check, and other than that, at boundary points you have to check. So boundary points now, like what? Okay, So for this, the sum that is going to be done is, one second, so f of x is equal, wait, which color, this one, white color, okay. So f of x, you have three piecewise functions, which is 2x plus 3, x plus 1, x plus 2, you can check. This is the question, okay. So for this, what you have to do? You have to recall. What do you have to recall? See, what do they give? What have they given? They have given you some intervals. See, for intervals, in sense, this concept you have to recall. But if in case it was pointwise, then which concept you have to recall? Okay, for sums like this. Okay, for sums like this, for this sums, what you have to recall? You have to recall this concept. Okay, so since it is interval, then you have to recall this one concept. Okay, so this is all we said, right? Now we are going to apply all these. Okay, so before going into this one sum, I have to say, whenever you are having at extreme points, okay, this is one extreme and this is another extreme, okay, whenever you are having, right, here you can see that it is less than or equal to, here you can see here also it is less than and equal to. Now see, here you can see that x is greater than or equal to minus 3, okay, and here you can see that x is less than or equal to 1, okay, less than or equal to 1. Here you can see that x is greater than or equal to minus 3. So when you are having equal to also here, when you are having equal to also over there, what does it mean? It means, just think a little bit, what does it mean? It means actually over here you have to use your one-sided continuity. So while using one-sided continuity where x is greater than or equal to 1, what you are going to use? You are going to use the same input. Okay, see, you are going to use the same input only for here. What is the input? Here you are going to use minus 3 only for the input, right? And also here also check where x is less than or equal to 1. Here also you are going to use the same input, which is 1. Here it is actually minus 3. Here it is 1. Okay. So in these two places the input is same, which is minus 3 for this place, and for this which is actually 1, right? So where you are going to give the input? Where you are going to give the input? For x is less than or equal to 1, minus 3, you are going to give it here. Okay, here also you are going to put minus 3, and here also you are going to put minus 3, and the function is also same only. So that means what? That means here it is going to be equal. So automatically it means that it is continuous. Okay, so at minus 3 and at which point was the another one, which was 1, right? Okay, so at minus 3 and at 1 it is naturally discontinuous. Okay, so you need not to check at 1 and at minus 3. So at remaining points only you have to check what are they. They are minus 2 and at 0. Okay, so let us categorize that. So first is x is equal to minus 2 and x is equal to 0. But we are hero. We are trying to be, at least. Okay, so f of minus 2 is it should be equal to f of 2 plus should be equal to f of 2 minus. Okay, instead of writing limits, I'm feeling very lazy to write limits. Okay, so like this you have, right? Now what you are going to do? First is f of minus 2. So let's calculate for f of minus 2. So this one you are going to use for minus 2, right? Minus 2, minus 2. Here also minus should be there. Here also minus 2 should be there. So put over there. So minus 2 plus 1. This only you are going to use. So here only equal to symbol is there. So that is why you are going to use this one for f of, okay, for f of minus 2. Okay. So for f of minus 2, which is equal to this one, which is minus 2 plus 1, which is equal to minus 1. Okay, next is this one. Okay, so which is plus, so x is x should be greater than or equal to minus 2. So here also you are going to use the same thing only. So limit x tends to x plus, right? So minus 2 plus of, what is the x? X is you are going to put, okay, f of x, which is limit x tends to minus 2 plus, so what is this? This is what you're going to put, x plus 1 which is equal to, now you put the value which is minus 2 plus 1 which is equal to minus 1. Okay, so then next is limit x tends to minus 2 minus. So here you are going to use this one function. Okay, so f of x is equal to limit x tends to minus 2 minus. So here you are going to use this function, right, which is 2x plus 3 which is equal to, now put the value which is 2 into minus 2 plus 3 which is equal to minus 4 plus 3 which is equal to minus 1. Okay, see, in all the cases it is minus 1. So that means it is continuous at minus 1. Okay, it is continuous at minus 1. Okay, then now what you are going to do is you are going to check at x is equal to 0. Okay, f of what color is this? Okay, so f is equal to 0, f of 0, not f is equal to 0, sorry, f of 0. So f of 0, now I have to use this function, right? So then that means x plus 2 which is equal to 0 plus 2 which is equal to 2. Then next is limit x tends to 0 plus, so for that means x should be greater than 0. Okay, no, we will take 0 minus first. Okay, 0 minus. Okay, 0 minus, so f of x which is equal to limit where x tends to 0 minus, what, this is what you are going to use, right? So which is going to be x plus 1 which is equal to, put in place of x 0, so it will be 0 plus 1 which is equal to 1. Okay, see, here it changes, here it is 2, here it is 1. That means what? It is discontinuous at x is equal to 0. Okay, so discontinuous. Here within that you can just like that you can say, but if you want, but you have to prove, you have to also get x limit x tends to 0 plus, that also you have to get, but we need not to get here I'm not getting, but in your answer paper you have to write. Okay, so continuous at x, sorry, discontinuous at x is equal to 0. Next is types of discontinuity. See, you have a few types of discontinuity. Haven't I taken notes? I should have taken notes. No, I have taken notes. 1 minute. One thing I forgot to say, what is that, and where was that question? This question, right? Here also, like this also you can do, okay, but this is what our NCT method is, but also in another method you can do, that is by using graphical method. Okay, you can draw graph for this equation and you can draw graph for this equation. Already I've kept the notes, right, so I'm not going to waste that much of time by thinking and drawing. See, if you want me to draw the graph, then at 1, then at 2. Okay, so the graph is going to be, one graph is going to start like this, okay, and another graph at the point of 1 which is going to be like this. You can see that it is discontinuous. Okay, so for this one line, one will be, for these two different equations you are going to draw different graphs. Okay, so now we are going to see types of discontinuity. Well, okay, so types of discontinuity. Okay, here you have to pay a lot of attention because this topic is going to be very amazing. That is, one is removable discontinuity and another is irremovable discontinuity. Okay, before that I will keep that notes. Okay, and even they are having some interest in intra-divisions. Okay, so removable. The next is irremovable discontinuity or non-removable, not irremovable. Irremovable, that is grammatically wrong word. Sorry, irremovable. Sorry, non-removable. Non-removable. I think it is wrong word grammatically. You can comment in the comment section. I don't know. Okay, non-removable discontinuity. Okay. See, what does it mean? It means you can remove. See, it has some discontinuity. For an example, you take this one. This graph is having some discontinuity, right? But you can, okay, in some cases, in some specific cases, you are able to take that discontinuity out and you can throw it and you can make that as continuous. That means you can take this point and you can place it here. Okay, you can throw it at the right place. So you can keep it, then it will be continuous. So at some points, okay, at some specific points, okay, at some specific points, it is actually like this. Okay, it is actually removable discontinuity. Okay, and one point that you have to notice here, over here, LHL, left hand limit, will be equal to right hand limit. Okay, which is actually which will be having a finite answer. Okay, and as I said that here this is actually having some intra divisions which are isolated point, and next is missing point. Okay, so now by name itself, many of you guys would have guessed it what it is. Isolated point and the missing point. That means, see, for us the graph is going to be like this, but whereas for this the graph is going to be like this. See, here the point is there, which means you can actually take that point and you can put here. But there is no point like that. Here the point is completely missing. So you can say that very easily by looking at this itself. What does it mean? It means LHL is equal to RHL, but is not equal to F of A. Yes, right. But here LHL, okay, here also LHL is equal to RHL. Actually, it is like a general case. Okay, LHL will be always equal to RHL in removable discontinuity, but is not equal to F of A, because F of A, the difference is here and here. Here F of A is finite, but here it is not finite. Okay, so it is in not defined. Not defined. Okay, so coming to the case of non-removable discontinuity. Non-removable discontinuity. What it is going to be? It is actually of a few cases. 3 different cases. First is finite, infinite, and oscillatory. Oscillatory is very special. Okay, oscillatory is very special. Which point? What color? Oh, thinking. Okay, so finite. Okay, finite, infinite. I like to hear the sound tapping of the board. Infinite. Okay. Then at last but not the least, which is very important, that is oscillatory. Okay, oscillatory double L will be coming. Oh, spelling is always telling me. OSCILLATO. Okay, first is finite. See, finite in sense like this, the graph is going to be. Okay, and note here you cannot remove that discontinuity and you cannot just place it at the right place, or you cannot remove that discontinuity and you cannot make the function as continuous. Okay, so that means the best example for this is going to be like this. Okay, like this. See, it's completely detached. If in case it was a point 9, it will be very easy for us to remove that one point, and you can do some magic, some torture, and you can make it okay continuous. But here you cannot do like that. Okay, so it is actually finite. Okay, and very easily you can see that LHL is not equal to RHL. This is L1. Okay, then this is L2. See, are they both equal? There's no chance. Chance is going to be 0%. Okay. Next is infinite. For this, if you want the graph, then the graph is going to be like this. See, the graph is like this, which is going towards the infinite. Okay, which is going towards the infinite. So it is actually infinite discontinuity. Okay, it is a type of infinite discontinuity. And here it is actually completely infinite. That means what is infinite? Here you cannot say like LHL and RHL because they are also non-definite. Okay, not defined. Okay, here oscillatory, I will first give you some examples, then we will be discussing oscillatory in a separate slide because it is very important. Examples are which color shapes? We shall be using this one, which is sine of, okay, sine of 1 by x and then cos of 1 by x. Okay, so for the case of sine of 1 by x, okay, so when we are taking about the graph, okay, so sine of 1 by x, okay, when you're taking the graph is going to be like this. Swank. Okay, like this only the graph is going to be like why? Okay, why the graph is like this? Why in this particular place alone it is like this much oscillating? Okay, this is actually a highly oscillating rate. That is why this is known as oscillatory discontinuity. This is actually from 0. Sorry, this is 1 by 2. Okay, this is 1 by 2, and then this is minus 1 by 2. Okay. Actually, it is highly oscillating between this fraction because over here you just check, you will be having what? You will be having between this portion, you will be having 3 by 4, or you will be having some numbers like 1 by 4, you will be having 1 by 5, you will be having 1 by 6, you will be having 1 by 7, you will be having, okay, all these will be between this portion, right, between minus, okay, and also you will be having minus 1 by 7, you will be having minus 1 by 6, you will be having minus 1 by 8, you will be having all these portions also will be there between this part itself. Okay, so all these are there. Now try to put each and everything there. So when you are putting 1 by 4, then it will be sine 4. Okay, then it will be sine 5. Then it will be sine 6. Then it will be sine 7. Okay, when you are putting this, it will be minus sine 7. Then it will be minus sine 6. Okay, then it will be minus sine 8. You can see that. Okay, normally in generally, if you are taking sine graph, which is like this now. Okay, sine 1 will be here. Okay, sine 1 will be here. Sine 2 will be with a little bit more space. Okay, then sine 3 will be with a little bit still more space. Like that, you will be having a lot of numbers with still lot more space, right? But here you are actually shortening that space. So as you condense and as you condense, here also it condenses, and also here also it will be condensed. Okay, here also it will be condensed. Like this also, here also it will be all condensed. So they all condense together because no matter how much values you put, they will be giving you some values which are like this, and the difference, okay, the difference between this value will be high. Okay, it will be kind of higher than having, like, if you take sine 1 by 4, okay, and you take sine 1 by 5, okay, the difference between this value will be lesser than the difference between this value. Okay, so it's going to occupy some large amount of distance, but since it is like this, like 1 by x, it should be condensed. Okay, it will be condensed. Actually this part is kind of tougher to understand. it's kind of a little bit higher order. It had taken me around 1 day. Okay, I was thinking, then something got into my brain. That is what I'm trying to say. Okay, then it will be condensed. All these point values will be condensed together, so it will be giving you this much oscillating. And also, when you use an app, for an example, you can use Desmok. Okay, so when you are putting this particular function in that sine of 1 by x, you cannot zoom it. Okay, as you zoom it, it will be just giving you this much. When as you zoom it, again it will be oscillating. Okay, and again it will be oscillating. Okay, and exactly at this point, okay, exactly at x is equal to 0, it is going to touch infinite. Okay, and when x is extending from positive side of 0, it is going to touch positive infinite. When x is extending towards from negative side of 0 and it is going towards this place, then it is going to touch minus infinite. Okay, so this is how this is actually. Okay, last but not the least, which is our intermediate theorem. Okay, kind of important, but no, one more concept is also there. Okay, next to what do we have? So theorems of continuity also you have. Theorems of continuity. That means when we are having like f of x and then g of x, okay, you are going to use some cases 3 and like this, right? So which is going to be